Today we have more exciting CS24 goodness, or badness if you will, because we do get into some technical details that are not as exciting today, but it's still pretty neat stuff. So we introduced CDECL last time. CDECL is a calling convention. Calling conventions are an agreement between the caller of a subroutine and the subroutine itself as to how different values will be passed and different shared resources will be managed and so forth. So this one, like I say, is used widely on Unix systems. It's not used on Windows, which is one of the reasons why we don't like using Windows for doing CS24. Windows uses standard call, and it's a little bit different, so we don't like to, we like to keep it all the same if we possibly can. And there are these shared resources, the stack and the register file. So we need to have the caller and the callee agree with how we're going to actually interact with these shared resources. So at these aspects of the calling convention, who sets up which parts of the call, what needs to be saved, who saves it, how to return values back to the caller, and who cleans up which parts of the call. So this was the basic gist of CDECL. And by the way, part of the reason why we started a little bit late is I threw the slides up, so if you happen to be the kind that likes to look at the slides on your computer as you go, it's there. And this would be a great slide to keep in mind as we go through the material today, because it'll have basically all the details of CDECL. So the caller pushes the arguments in reverse order, which is a little bit weird, but that's what it does. There's some really good reasons for it. So the last argument is pushed first, and then the next argument is pushed, and then all the way down to the first argument. So you can see that the earlier arguments have a lower address on the stack because the stack grows down. And later arguments have a higher address, which does help conceptually to keep track of everything. Okay, so the caller uses call to invoke the subroutine, which pushes the address of the next instruction, or the instruction that the subroutine should call to or return to, onto the stack. So that would be retadder at address 5C hexadecimal. And then the callee does the standard thing, which is not required, but it is a really good idea. Sets up a stack frame, or a frame pointer is really the better name for it. So we push the old value of EBP, because that was the caller's EBP, and then we set our EBP to be our current stack pointer. So now that becomes the frame of reference for everything else. So push EBP, move ESP into EBP. So now arguments are going to be at positive offsets from EBP. So 0 EBP, or just EBP in parentheses, would be the caller's version of EBP. 4 EBP would be the return address. And then everything after that is arguments. So 8 EBP is the first argument, 12 EBP, and so forth. And then if we decided to allocate space on the stack for local variables, which happens rarely, I have to say, then we can store those in negative offsets from EBP. So minus 4 EBP, minus 8 EBP, and so forth. And I kind of mentioned this before, that what we really like to do is use registers, because registers are the fastest memory to access, or I should say that it's the fastest memory that our programs can access on the processor. So if we can use a register, we'd like to. If we can't, if we run out of space, because we just have so many local variables that we need to work with all at the same time, then we can use a stack for those as well by subtracting some constant from SP, and then that makes space for us, and we can start referencing those with these minus 4, minus 8, and so forth. Okay? So are there any questions about this slide? Because CDECL is extremely important. We're going to be doing so much with CDECL as we go through the term. Okay? So these are the caller and callee save registers. It would serve you well to memorize these. So EAX, ECX, and EDX are caller save. And what that means is if the caller puts a value in one of these registers and wants to get that value later after the subroutine returns, the caller is responsible for saving it somewhere, typically onto the stack. Okay? And obviously if it saves it onto the stack before pushing all the arguments, the callee will never know. It's perfectly fine. The callee save registers are sort of analogous. So we have EBP, EBX, ESI, and EDI. Those are the ones that the callee is supposed to save if it changes them. Because the caller may have values in there that it needs, and if it does, the callee can't muck with them without saving them first. So that's why we always push EBP and then set ESP to EBP. Okay? So keep those ones in mind, because you will see that a lot. The callee saves the return value into EAX if we have one. If we don't, we can use EAX to do computations. It's super simple. Okay? And so this is what you frequently see at the end of subroutines, move EBP back into ESP. And if you think about it, if we have ESP lower than EBP, we may have some local variables or stuff we've done on the stack. And setting ESP back to whatever EBP was just throws all that away. So you're sort of chopping down the stack back to where it was before when we set up in our subroutine. And so then we just pop the old value of EBP off the stack. Notice caller EBP at 5.8. And then we return. So we pop caller EBP off, and then the stack pointer points at the return address. We ret, that pops the return address off, and now it's up to the caller to clean up the arguments. And it can do the same thing. It could either do pop, 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 or it could just add a certain amount to ESP to just throw away that space on the stack. You'll notice this at this level of programming, that we don't necessarily always use the formalisms. We don't always use the abstractions. If I have 5 arguments to get off the stack, it may be faster for me to add 5 times 4 equals 20 to the stack pointer than it is to call pop 5 times. So I may just do that. Okay? So you have these kinds of things that will happen at the assembly language level. You just need to understand conceptually what the model is, and then when you have these various ways of doing things, it'll all make sense. Okay? Does that make sense? Like I said, as we go through other things, it might be helpful to keep these slides open on your computer while we talk about them. Okay, so we had this C program, which we introduced last time, which was a very simple accumulator. You probably wouldn't write it this way because if you have one accumulator that's helpful, it might be more helpful to have 2. And we can't really do it this way because we have a global variable. But we have a couple functions, accum, reset, and then main, which exercises some things. We already talked about this code a little bit last time, and we're going to start looking at how this is implemented in IA32. What we will do is not write it ourselves, because at least it's nice to see that these ideas actually hold. So we're going to ask the compiler what it would write. And the way that you do that is to give it this -S argument that I have up here on the slide. And that'll generate a file called amain.s. Just happens that we called our program amain for accumulator main. And so amain.s will contain the output of the assembly code. And then we also have -O2. What this does is tells the compiler to try to optimize a few things. Because it turns out that the first cut of the assembly code that the compiler generates is horrible. It does all kinds of stupid things. And so what happens is you have various phases of compilation. And I wish we had a compiler class because it's really cool. But you have different kinds of optimizations, different phases of optimizations, and the compiler goes through and says, oh, that was dumb. I can fix it and make it faster this way, or I can fix it and make it faster that way. So -O2 applies some common optimizations so that our code looks a little bit less dumb. And these results do vary widely. If you look at the SIGWIN output, for example, it will probably be significantly different. If you look at OS X's output, it will be very different. But there's some really interesting things that OS X does just by virtue of the way the operating system is designed. So if you're curious, let me know, and I will be happy to describe those things to you. Because there's some techniques in there that you see in much more advanced systems programming just because of the way OS X is designed. But we will look at the Linux output. So here's some of the output. It obviously goes further down than this. But we have these various details in here, and some of it we recognize already because we understand assembly language syntax. So we have move L, and we understand that L means that it's a long word or a 32-bit value, ESP into EBP or whatever. We recognize these things. But we also have other lines that start with dots, stuff like that. And these are assembler directives. It's just like in C or C++ where you have hash marks or pound marks or whatever you decide to call them in front of certain symbols, where it's basically saying this is a preprocessor directive. So these are assembler directives, and .text is a really important one because it says this is where the program text itself starts. It's kind of historical reasons why we call it the program text, but we won't get into that. And then we have labels like accum and reset, and we recognize those as well because those were what we called our functions. So these are labels, and you can imagine that the assembler, as it's going through this, it's going to associate accum with an address. This is the address of the code for the accum function, so that when I want to call it, Yeah, I can say call accum, and it will generate the corresponding call, and then whatever that number is that I don't know, I don't care, the compiler can deal with it. Okay, and there's a few other ones as well up here that are kind of important. You can see that .type says this is a function or this is a variable and so forth. You also have these .p2 aligns, and .p2 align basically does alignment with certain addresses. So for example, p2 align 4, 15 says I want this to be aligned on addresses that are at 2 to the 4 boundaries or 16-byte boundaries. And I want to move addresses or code, I want to move it no more than 15 bytes. So you can see it's just aligning it on 16-byte boundaries. Okay? So pretty straightforward. I should also mention that the global is really, really important. And notice that it says globl. It doesn't have an A. I don't know what they have against A's. But it's global accum. What we're saying is this symbol should be visible outside of the generated code, because it's a function. I need to be able to call it. But if I had labels internally inside my code, I don't have to put .global on them, and then they're not accessible outside the generated object file. So those are just a few details there. If you have any questions, you can always ask. You'll also notice like the .size at the end. .size, accum, comma, hyphen accum. What in the world does that mean? Well, turns out to be the current address in the code as I'm generating it. And so what we're basically saying here is the size of this accum function is the current address minus the accum address. Pretty obvious. Okay, so anyway, we have these various things that we do here. Why does it do P2 align? Because there's no guarantee that accum's function is going to have a multiple of 16 bytes in the implementation. So it's funny, but we normally prefer to waste space instead of time. Time tends to be something we have more difficulty actually generating more of than space. And so in general, when you see programs and so forth, you'll notice that they will happily sacrifice space for time.
Well, just to double check, does that imply that P2 align only applies to the current function?
Yeah, P2 align, what it does is it basically inserts space between the thing that preceded it and the thing that follows it. So yeah, it probably applies to data values and variables as well. I haven't ever tried it, but in this context, obviously it applies to functions or code. Any other questions? All right. Let's see, global variables. So this is at the end of the output, and you'll notice it has various things like .ident, who generated this function, and so forth. And we have this .com thing. Oh yeah, so .size main, .minus main is the end of our main function, so big deal there. And then we have that global variable value. And again, we say, here's a symbol named value. I don't know what address is associated with it yet. I don't care, because the assembler takes care of that. And we're saying it's 4 bytes, and we want to align it on a 4-byte boundary. So that's basically all we have here. And then the address will be assigned to that, and then everywhere that we save value in our assembly program, the actual address will be replaced into that space in the generated machine code. Okay, so that's pretty straightforward, but that .com is just a common symbol or a common variable. Okay. Why is it defined at the end? It really doesn't matter where it's defined in the assembler, because these end up going into different places in our program. Programs actually, I don't know how much I want to get into this right now. Ask me after class. I have a real problem with getting derailed by interesting side topics, so I'm going to just go on. But yeah, it doesn't really matter where it's declared, because it'll end up in a different space in the program anyway, and I'm just going to leave it at that for now. Okay, let's see. So this was our accumulator function. How many arguments does it have? It has 1, right? And it accesses a global variable, so and it returns a value. So we know that it's going to have an argument pushed on, cdecal and all that. It's going to have a value in EAX coming back, and we'll manipulate this global variable. So this is the code that's generated by the assembler. So notice we set up a stack frame, push EBP, and then move ESP into EBP. And then we get N off of the stack, so move 8 EBP into EAX. we add the current value into EAX, and this is where the compiler is kind of nice and it's clever. We know that we need to return a value. We need to return the value after accumulating into it. So we'll just load our n into EAX, add value into EAX, and then store value back. Yeah, so move EAX back into value. So that's what we do there. And you'll notice pop EBP and return. So it's very straightforward implementation. The only little nuance here is that you'll notice that we probably, like if a human being was writing this, you'd probably put the pop EBP right next to the ret. Okay? And the only reason that the compiler might do it differently is just because of its internal model of what the processor's capabilities are and how it might be able to pipeline these instructions and execute them a little faster. So the compiler might know, well, if I do the pop before the move and then the ret, then that might be slightly faster than doing the move first and then the pop and the ret. So that you notice these kinds of nuances when you look at generated assembly code, that sometimes operations will not be succinct and sort of separated from each other. They'll be interleaved a lot more because the processor knows how, or not the processor, the compiler knows how the processor might execute these instructions more quickly. Okay? So that's a cum. That one was the easy one. Oh yeah, so I had a picture of a stack. That might have been helpful. Yeah, so remember, caller EBP is always at EBP 0, if you will. And then 4 EBP is going to be the return address, and then 8 EBP is the first argument. Okay, let's see the reset function. So again, we pull the old value out, and then we set value to 0. And this is the code generated for reset. So we push EBP. Again, we have this unusual interleaving where we move value into EAX because we know we have to return that. We move ESP into EBP. Wait a minute. Then we pop EBP and we ret, right? We don't need EBP at all in this function, right? Do we ever use the frame pointer anywhere in this implementation? So you can see that not every function requires a frame pointer. Reset doesn't have any arguments, and so that at least should give you a clue. I don't need a frame pointer in this context. So we could eliminate the push EBP, the move ESP EBP, and the pop EBP. And then our function would only be 3 instructions long. It would be a lot nicer. It would be probably twice as fast. All we really need to do is move value into EAX, move 0 into value, and ret. That's really all we had to do. Okay. So again, you'll notice this. If we were to write this function ourselves, we'd do a better job. If we were to apply a higher level of optimization in the compiler, we would see this get much better. So if we did something like -03 or -04, then you would definitely see this kind of code eliminated because there's no point in having a frame pointer. All right, questions? Yes? Yeah, so what happens at the end? That's a complicated question too. I would love to spend some time answering that. What happens is so you have different phases. You have the compiler, which translates C code into assembly code, and then you have the assembler, which translates assembly code into machine code, but it can do this piecemeal. So we have multiple source files. Each source file can be turned into its own object file. Who's heard of object files? Probably a lot of you by now. So those object files, you can't just run the foo.o and have it load into the program, or, into the computer and start running, because the addresses haven't all been fixed up and fully assigned. So there's a final phase called linking, where we take all those .o files and we stuff them all together into a single executable, and then that thing is the thing we can actually run. And it's at the link time that the actual address of value is computed. And then that's plopped in everywhere that it says value. So that address might be, I don't even remember where we normally stick those things. I used to know this, 804.8000, so it would probably be like a hexadecimal value 804.8 something would be the actual value, and that would be plopped into the machine code somewhere. Okay. Which is pretty groovy, especially if you wrote the compiler and assembler yourself. But other than that, it's not very exciting. Okay? Any other questions? All right. Let's see, the main function. So first thing I want you to look at is how many function calls do we have here? Well, we have reset, we have rand, and we have printf, and we have accum. So there's 4 functions being called. Which function takes the most arguments, and how many arguments does it take? In our context. You're right in general, but yeah, printf, it is bounded because we need memory for it. But yeah, printf in this context, how many arguments do we have? Yeah, 3 arguments. That was a good general answer. I liked it. So, and how much space do those 3 arguments take? Well, we're going to pass a char star, so that's 4 bytes. We have n, that's another 4 bytes. And we have whatever accum returns, which we know is also 4 bytes. So 12 bytes is the amount of space that the largest function calls arguments are going to take. Okay, what else do I want to bring out here? We have I and n. Is that going to wipe out all of the registers that we have available to us? The answer is definitely no. So we really don't need space for local variables for this function. We need space for calling other functions using cdecal, but we can stick I and n into registers. And that's in fact what the compiler does. So this is the first part, and I'm not going to spend a lot of time talking about most of this code because it actually goes into much more detail than we really care to at this point. But you have these first 2 lines in the main function, which basically, again, align the top of the stack with the 16-byte boundary. Why would we do that? Well, if things are aligned, they're faster. And we'll talk about why in a few lectures when we actually talk about word-aligned memory access. But right now, you'll just have to take my word for it, or my D word or my quad word. So, but this is all we do. We word align the top of the stack, or 16-byte align the top of the stack. Then we have our standard push L EBP, move L ESP EBP. So that sets up the frame for main. Now, we don't actually access the arguments of main at all. You may be aware of that. You can have up to 3 arguments for main, argc, argv, and an environment pointer. We don't really do that here. We just say main. So anyway, we don't really need a stack frame here either. Then we have call save registers. So ESI and EBX are both call save. ESI happens to be the register that the compiler assigns to the variable I. So I starts out as 0 for I equals 0. So you can see it's cleared with an XOR. XOR ESI, ESI. Okay. Now the next thing you see is kind of unusual. Notice we subtract 12 from ESP. Again, we don't need to set up space on the stack for local variables because we have enough registers. But we do need to make function calls. And so since 12 was the amount of space that the largest function call would take, we just go ahead and subtract 12. The compiler is pretty fast and loose with the stack, you'll notice. Okay? The first thing we do is we clear the accumulator. Now remember, reset returns something in EAX, but we don't care in the way that we've written this code. We haven't said like n equals reset or anything like that. So it just calls reset, and that's it. We don't have any arguments or anything. So we invoke reset. And then this is the remaining code after the reset. And this is basically implementing our for loop. So you'll notice here, .L6 is the start of our for loop. And I said that ESI is the variable I. And you'll notice in our for loop, for I is 0, I is less than 10, I plus plus. Well, the compiler is like, nothing else refers to I, so I can increment it whenever I want. So it does it right away. Notice the red line, add L 1 to ESI. Now it could have add L'd it. It could have incremented it with an inc L, or it could have done an LEA. It could have done a lot of different things for updating ESI. But we're not. We just went ahead and added 1 to ESI. Then at the end, with our red code, we say, hey, how do we fare when we compare ESI to 10? If it's not equal to it yet, go back to the top of the loop. Okay, and so it just loops 10 times. So that's the red code. That implements the flow control specifically. Now I say here that EBX is n. I don't have anything here for that, but we'll go into this in another step or two. You'll notice that all of the purple code, it looks kind of purple. You can tell at least it's a different color than the black of the normal instructions. But that code implements rand %1000. What we're doing is we're taking the modulo 1000. If I were to say to you all, hey, I want you to compute rand modulo 1000, then what you'd probably do is call rand. You know the argument, or the return value comes back in EAX. You'd probably then set up some kind of div-l 1000 or something, and then actually you should probably clear EDX to make sure that that doesn't screw things up, and then do our div-l 1000 or whatever. And that would be fine. But you can see that the compiler said, I'm actually going to jump through a whole bunch of hoops to do this instead. The reason why is that all of these instructions are actually collectively faster than doing div-l 1000. Div-l is one of those things. It's just like the machine code that you guys had to write for the first assignment. Division takes time. And most processors can't do it very efficiently. But there's all kinds of crazy math tricks that you can use instead. So like I say here, integer division and modulus can actually be implemented as multiplication. And so that's what compilers often do. And if you're curious to understand the technique, there's the book that you should look at, Hacker's Delight. I have a copy of it. If you happen to be really intrigued by how to do all these kinds of crazy bit manipulations or compute math really efficiently on the processor, get that book. It's worth it. Okay? So we won't go into it any more than that, but you can see that there's a lot of crazy stuff going on. And we will not talk about it because it's scary. It scares me. So anyway, then we have these last parts. Anyway, the whole point is that EBX ends up being 10. I'm sorry, EBX N. It ends up being N. I just completely misspoke. So notice we have move EBX ESP. Okay? We're sticking the value in EBX into where the stack is pointing. And then we call a cum. This would be identical to saying push EBX and then calling a cum, except that the compiler decided, I don't want to actually work with the stack very much. I just want to allocate space for 12 bytes. And then I know a cum takes one argument, so I'll put it where it needs to be and then call a cum. And now the answer from a cum is in EAX. And so we have our call to printf. And printf has 3 arguments. The first one is our string constant, so that's .lc0. You can see it moves it into where ESP points. For ESP is going to be the second argument, n, so EBX is stored there. EBX goes into for ESP. And then EAX, yeah, that's the return from a cum n, goes into 8 ESP. Okay, all the world is right. And then we invoke printf. Okay. So it's kind of interesting. The compiler doesn't really do things the way that human beings do them. And as an aside, you can usually tell the difference between compiler-generated code and human being-generated code very easily. Because human beings just don't like to think this way. We like our abstractions. They help us to comprehend what's going on a lot more efficiently. Okay? So, but the compiler is happy to do this kind of stuff. Any questions? All right, I just want to give you, this is sort of, you can think of this as being the orientation for what the compiler will generate, so that if you do have to look at compiler-generated code, you will understand generally some of the patterns that you will notice. This crazy math junk, well, we can do things faster if we do them in sort of unorthodox ways. Okay? It will generate the correct answers, but like I said, it's a trick that goes much faster than if you were to do the division directly. And the same thing with manipulating the stack. This is very common for compilers. They'll make space on the stack, throw a bunch of values in there, and then call functions, as opposed to pushing and then popping. Okay? You see a lot of shortcuts taken with stack manipulation. All right? Yes? Can GCC optimize human written assembly code? No, I don't believe that it can. Yeah. I suppose that what you could do, if you really were curious about doing that kind of thing, is explore LLVM. Because then what you could do is give LLVM a series of assembly instructions and then have LLVM's optimization take a crack at it. But I've never tried that, and so you'd have to let me know if anybody decides to try that, because that could be really fun. That could be cool. It may not be able to optimize stuff like this, because unfortunately, at this level, what you're seeing like this. If you had div L1000 there, maybe it could go ahead and optimize it. But frequently what you'll see is that compiler optimizations depend on information at the higher level language level and also at the assembly language level. They rely on both of those. So semantics of the higher level language will be leveraged at the assembly language level, which is why sometimes you see things like, I don't know, is anybody here like really interested in security and encryption? Is anybody like super excited about that kind of stuff? So sometimes what you'll see, for example, is I load a password or a passphrase or a private key into a buffer, and then after I'm done with it, I decide to erase the buffer by setting it all to zeros. And then I never access the buffer again. And unfortunately, with our modern optimizing compilers, they look at what is done with variables and they say, you know what, you set this buffer to some values, the compiler doesn't care what they are, and then you never access it again. Therefore, I'm going to eliminate that part where you set it all to zero. And it'll keep going back like that. So, and even if you have a function that may have undefined behavior, it'll assume, well, surely they would never write a function that would behave in an undefined way, so I'm going to assume that it behaves in a defined way and then figure out what stuff earlier on I can just eliminate based on the presumption that this other stuff would cause undefined behavior. And so you can have compiler optimizations that generate very different code from what you write, and in fact completely wrong code. And it's because the compiler is leveraging semantics at the higher level. And the human being may not be familiar with all those things, and that's why the compiler's output is different than what the human expects. So there's some unusual and frustrating and unfortunate realities there that you get into when you get into more advanced programming. Okay? That's all I'm going to talk about that for now. Although, again, that could be a whole lecture by itself. It's fascinating stuff. I just read an article on Reddit about how we sort of assume that when you have a semicolon between two lines of code, that the earlier line of code happens before the later line of code. And you already saw how some of these things are interleaved. The I++ semantically goes at the end of the for loop. The compiler moved it all the way to the top of the for loop. It's like, I'm going to do that first. And there's a lot of other more subtle situations where you can run into those issues. It completely interferes with writing operating systems and concurrency systems. Okay? So you have to be really aware of that. But not in CS24. We don't care. Take 124 and then your life will suck. Okay. All right, let's see. So we needed a string constant for printf. And so before main, you would notice that there would be a .lc0, and it would be set to the string constant. Now, what's its address going to be? Well, that actually will live in a slightly different place in your program besides the code and the data you can write to. And again, we don't really get into that at this point in the class, but some address will be assigned to it, and then .lc0 will be replaced with the corresponding address at compile and then link time. Or I should say assembly time and then link time. Okay? Let's see. Now, are there any questions about this? Any other questions that don't take me 5 minutes to answer? I said there's so much interesting stuff. I wish we could go through it all, but we can't. Let's see. So we are going to assert, because of the nature of cdecl, you'll notice that each function call has its own area of the stack that it works with. Remember, we call that the stack frame. We reference it through the frame pointer, or EBP. Like I say, the caller pushes the arguments onto the stack, calls the callee. The callee saves the caller's frame pointer. We have an agreement as to what registers can be mucked with and which ones cannot be mucked with. And the callee makes sure to restore all of the state it's responsible to store before, or I should say to restore before it goes back to the caller. And so this allows us to do recursion very easily, because each recursive invocation sets up another frame on the stack. So we can we can have each function's state be separate from all other function invocation state, even though it may be the exact same function. Okay? And I think I have a little note here. If you have already started assignment 2, you probably have recognized, I think it's fact, like the factorial function, you have to figure out how that would execute 3 times, okay, not 45 times or something really rude, and just see how recursive invocations work. Okay? So, yay for recursion. By nature of the way we define our convention, we can do recursion very easily. Okay, now the next thing I want to talk about is flow control. we have a whole bunch of these different flow control statements. We're starting to ease up the abstraction hierarchy again. And so some of this stuff, I'm not going to tell you exactly how we translate it into machine code because we don't care anymore. I'll show you how to translate it into pseudocode, and then you could translate that into assembly code easily, and then we rely on the assembler to take care of the rest. So if test expression, then statement, else statement. While loop, so while test expression, body statement, or for loops or do loops. These are easy to use. They're nice abstractions for flow control in our C programs. So what we want to look at next is how we translate these into IA32. And like I say, it does help us to understand what the compiler generates, especially when we're trying to understand the assembly code it generates. And it'll also help you because usually I have, a couple functions. By the time you get through midterms, you'll have written 2 or 3 functions that are a little bit more involved in IA32 assembly, so you can see how the whole process works. So typically we implement these with a series of conditional and unconditional jumps. So something like this, if test expr and so forth, we might translate it into something like this. If test expr is more complicated than just a variable access, we compute the result of the test expression, and then we basically say if that test expression, whatever it is. Maybe we have to invoke a function, and it'll be in EAX. The result will be in EAX. Or maybe we have to do some bit logic like we've had in the past where we had to compute certain things. So if T, then we go to the true branch, do the then statement. Otherwise, we fall through to the else statement. And then after that, we have to jump over the true branch. Okay? You can see that there's a lot of sort of hopscotching around when you do these things. And that's what makes it a little bit complex. For example, if we just said if test expr then statement and we didn't have an else, then probably what we do is say T equals test expr, if not T, go to done, and then fall through to the if branch. So you just have to think about how you might do this. I think I have a little note here that, the compiler will generate a whole bunch of different varieties of things based on what makes the most sense. Okay? So that's if statements. They're pretty straightforward. Do while. Who here has written a do while loop in the last year? Okay, I'm impressed. More than a few. They're much less common than while loops. I think everybody would agree. Like I write while loops all the time, and then I write maybe 2 or 3 do loops a year at most. Okay? But do actually is easier to translate than while. So we have a do and then a body statement, and then we have the test at the end. So we can just translate this as I have here. So we have a loop label at the top. Whatever the body statement is, we translate that into assembly code. We compute our test expression, and then if it's still true, we jump back to the top. Otherwise, we fall out of the loop. That's how we describe it. We fall out of the loop. Okay? So, excuse me. Do loops are pretty straightforward. While loops are like I say, are much more common, but they're more involved when we translate it. Because notice what we might do if we just did this naively. T equals test expr. If not T, go to done. Then we do the body statement, and then we go back to the top. Okay. Well, the problem is now we have 2 flow control instructions that we execute every time through this loop. And that's a bit of a drag for the processor. Processors, it turns out, hate flow control. Unconditional flow control is a little bit better. Processors have gotten so smart, I have to say. You kids are spoiled, that's what I would say. Because when I started programming back in 8th grade, we didn't have processors that could do like look ahead and branch prediction and all that kind of crazy stuff. And we liked it. So, okay, rant mode off. So, but basically, anytime you have a branch in your program, especially conditional branching, then you have a problem because the processor doesn't know which branch is actually going to be the one that's followed. But what it would like to do is keep prefetching instructions and doing as much as possible so that everything can be pipelined. That's fast. So what if it comes to a branch and it follows one side, and then during the actual execute phase of the instruction, it realizes, oh man, my prediction was wrong. Yeah, it's got to throw all that work out. That's slow. And then we have to start fetching the other branch and doing those kinds. So it basically is a pipeline stall. And that makes us sad if we're trying to write really efficient code. So conditional branching is especially bad. Unconditional branching is not so bad, but we have more caching issues. which we'll talk about in week 5. And so they're not as horrible, but they're still pretty bad. Okay? So the less branching we do, the better. The more happy we are. Now, that all said, processors are incredibly bright. They're like brighter than I would be as far as predicting branches. And so a lot of times when you have loops like this, you shouldn't worry about, oh no, it's got branches and stuff in it. I'm going to be, really slow. A lot of times the processor will have at most 2 branch prediction failures. They'll have one at the beginning of the execution of the loop, and then after that it'll be like predicting correctly until it gets to the end of the loop, and then it'll be like, oh, I was wrong again, and it exits the loop. So this branch prediction stuff is really good by now, and so if you have loops that execute for a long time, processors are like, hey, no problem. Okay? So the other thing too is that the compiler will frequently try to lay out code based on its best guesses as to which cases will most likely be true. So the compiler will also try to help the processor as much as possible to make these things fast. But all that aside, the whole point is that branching is a little bit slow and we'd like to avoid it. So what we'd like to do is figure out a way of taking this while and turning it into something we can do faster. And like I say here, we could always unroll the loop once. So we do something like this. We're actually not really unrolling the loop. We're actually just, like I say here, peeling off the first test. So we're kind of half unrolling the loop, if you will. So we say if the test expression is false, go to done. So we just skip the whole thing. And then we turned our while into a do while, which will only have one conditional operation in the loop. And we know it's going to be much faster and easier to translate. So this is a very common translation. Okay? And just continuing this, so we had if test expert, well then we could just say t equals test expert. If not t, go to done. So we're saying if we already need to skip the loop, just jump over it. Then we go into our loop, we do our body statement first, because now we're a do while instead of a while. We compute our test expression, and if it's still true, we go back up to the top. Okay? Any questions? Now, as an aside, when you write assembly code, I may give you pseudocode. I may just say, hey, here's an algorithm. I want you to implement it. What you should start out with is writing C code or some kind of C-type pseudocode, maybe Python-type pseudocode, if you will, and then go through these steps of progressively translating it into assembly code. It makes it much easier to understand what you're doing. Do not sit down and just start writing, move EAX, ECX, move EBP. You will have a non-working program, unless you've been doing this a long time, and then you've got about a 30% chance of having a working program. So, so just do what the compiler does. It does these phases for a reason. It makes it easier. Okay. For loops, so those are more sophisticated while loops. Notice we have initialization, a test, and an update. So that is equivalent to this translation. So with obvious scoping issues aside. So initialization, then a while loop with the test expression, and then body statement followed by the update expression. Okay? And we know how to do all of these things. Like it says here, we transform our while into a do while. And we can, just the rest of it goes where I have it up here. Okay. So it would translate it into something like this. Initialization, we peel off that first test, so t equals test expert, if not t, go to done, and then we have our do while. So body statement, update expression, and then we test our test expression again, and if it's still true, we go to the top. Okay, questions? Pretty straightforward. It makes sense to me, so hopefully you guys will get it as you go through this. So that's nice. Now we can do flow control. We've clambered up, so now we're at basic intro C-track programs. We can do those, yes. So that's nice, but then we start running into more advanced concepts. I like to be able to write this function. I want to give it n, and I want it to give me a list or an array of all the prime numbers between 2 and n. How many is that? Yeah, it is variable. And we have another interesting issue. So I'm going to throw that up there because that nails it. Okay, we have a variable amount of memory that we require for this function. But there's another issue as well. If I tried to store the answer on the stack, where would I store it? Yeah, the answer is not the stack, right? I mean, we just can't store this on the stack because remember that if we allocate space on the stack, that memory's lifetime is the lifetime of the function using it. So we have two issues here. We need a variable amount, and the lifetime doesn't fit in the way we manipulate the stack. So we switch to a new area called the heap, just like was mentioned. Okay? And this is a general area of memory available to the entire program. Now, what I should say here is it's kind of not entirely clear how I stated here. A large resizable pool of memory for programs to use. Every program has its own memory heap, which means that when you run your CS24 program and it seg faults in a big ball of fire, is not going to crash your web browser or your PDF viewer or anything like that. So every program has its own heap. But the heap is for much larger allocations. Programs request blocks of memory from this heap, and when they're done, they have to release them. So we have a very simple runtime facility now. We don't have a lot of capability here. It actually turns out to be pretty sophisticated when you look into how they're implemented, but all we're saying is give me a chunk of memory, and then when I'm done, I'll give it back to you. So these are the C standard functions for manipulating the heap. Who's used malloc? Who's had problems using malloc? Yeah, I love that. Malloc's fun. Who's had a program where they used heap allocated memory and it seg faults on some function return? Yeah, you get into all kinds of fun stuff like that. Who's corrupted their heap? You could go on and on. So anyway, like I say, allocate a block of memory using malloc. So what comes back is an untyped pointer, which means we need to cast it to some typed pointer to manipulate it. Okay, but like it says here, returns a pointer to the block of memory, or if it can't find a block that size, it will return null. Then we have free, where you handed a pointer to a block that you previously got back from malloc. And the heap's bookkeeping details are updated to say this chunk of memory is now available again for a subsequent call to malloc. Okay? So these are the two functions we can use. So, and this just sort of reiterates the things I was saying before. I don't want to spend too much time on this because I want to make sure we get to this all. Stack space is automatically reclaimed when functions return. So the stack is managed automatically for us by procedures, by the instructions we write for the procedures. Okay? So the compiler takes care of managing the stack properly. And we can do that because most of the time a function's local variables and arguments and return types, all of that stuff is fixed at compile time, so the compiler can emit instructions that deal with this stuff properly. Okay? Heap is very different. Frequently, the actual memory use required depends on input arguments. Like, I get n, and I have to find all the prime numbers up to n. And so programs have to explicitly allocate this. So this is something that the human being has to encode. It can't rely on the compiler to encode it for them. Okay? So make sure you understand these differences. Yeah, so we have a variation. Oh yeah, we want to do our vector add. We talked about vector add way back when we were showing how bad our processor sucked. And so we have A, B, and length, and we want to add those two vectors together into a newly allocated result vector, which you can see result equals malloc, length times size of int. We can allocate a result vector from the heap, so we don't have to store it on the stack and run into all the issues with that. We can just computer value, and then the caller can figure out when they want to release the memory. The memory will last beyond the lifetime of the function call. So we're going to look at that next time. We obviously don't have enough time to do that here, but I do want to point out that clearly pointers and arrays are related. They're like siblings, because we have result, which is declared as int star, and we access it as an array, just like A and B. So we're going to spend a little bit of time talking about this. Keep in mind, of course, C arrays, you probably all understand this. They're completely homogeneous. Every element is the same. So they're all the same size, and we access them with an index. So in C, when you have an array declaration like this, some type, array name, some number of elements. What this does is it allocates a contiguous region of memory. Now the compiler is what is doing the allocation. It is statically allocating this. So n times size of t bytes for the array, where size of t is the size of each element. It's a built-in function. It's evaluated at compile time. It's not a, I mean, you can call it, but it's just the compiler is going to say, oh yeah, that thing's 8 bytes. That thing's 16 bytes. It'll just plug that number in. Okay? So A is going to be, this is the array name, is a pointer to the start of the array. So now we can use A to access elements of the array. Okay, so what address does array element I reside at? Well, remember, it's an element, so we need to do something like A plus I times the size of the element. We need to do something like that. Okay? So element I is A plus size of t times I. Okay? And so that's exactly what the square brackets operator does. When you say A square brackets I, it does this math. Okay? So let's look at just a few more things and then we'll wrap up. C also has this weird pointer arithmetic thing, and this is where it gets a little bit weird. But when we say T star P, so P is some pointer of type T, we can add 1 to that pointer. But it doesn't just add 1 byte to it, it adds 1 element size to it, or 1 size of T to it. Okay, so like I say here, P plus 1 advances P 4 bytes if P is a pointer to an int, because ints on IA32 and GCC is 4 bytes. The same is true for subtracting. If I subtracted 1 from P, it would move back 4 bytes, even though I'm only subtracting 1. Okay? So you can think of that as being a number of elements offset. So an offset n from a pointer T will move forward or backward n elements. So this A square brackets I is identical to saying A plus I in parentheses and then dereferencing that pointer. Because remember, A is a pointer. We're adding an offset to it. That gives us another pointer, and then we dereference it to get to what the pointer points to. Okay? Does that make sense? I sure hope so, because you're going to run into this a lot. In fact, you're going to run into it a lot when you start writing your own allocator. Okay, so I'm going to skip this slide because we don't care. You can talk about that or look at that in your own time. So like I say here, how do we implement this function in IA32? What we're going to do is next time, we will implement this from scratch, including the call to malloc. And notice we have no error checking, but who cares at this point? And we'll go ahead and pick that up on Wednesday.